Everybody. So we've got another little strategy for limits here, something called L'Hopital's rule and indeterminate forms. You might see L'Hopital written a little bit differently. I've seen alternate spellings to this, but in any event, it's a pretty famous strategy you have for solving a particular kind of limit when we have something called an indeterminate form. So let's start with an example. And then we'll see what all this is about. So I'm going to start with the function f of x is equal to 3 natural log of x over x squared minus 1. Okay. Now notice this function is not defined at x equals 0 because we get that 0 in the denominator. So if this function meant something to us, right, if this described something important to us, we might be interested in what's happening as we get close to, sorry, not at x equals 0, geez, at x equals 1 because we get a 0 in the denominator, pardon me. So not defined at x equals 1 because we get a 0 in the denominator. So if we care about this function for some reason, if it describes something of interest to us, even though the function is not defined there, we might be interested in what's happening as we go towards that point. It might still tell us something good information. So we might be interested in taking the limit as x goes to 1 of 3 natural log of x over x squared minus 1. Well, if you take the limit of each of these pieces individually, you get 0 over 0. Right? And I can't stress this enough, 0 over 0 is not 1, right? You might have a limit that sometimes looks like 0 over 0, and if you do some manipulation, you get 1, but as a rule, you can't decide that 0 over 0 is equal to 1. It's not defined as a number, and in terms of limits, this is what we would call an indeterminate form because it doesn't determine for us anything about the limit. Right? We don't know now if this limit exists or not. And if it does, we don't know what it is, right? We could still have a situation where the limit doesn't exist, or we could have it be any of the infinite real numbers. So we really don't know if it's indeterminate form. Okay. Further, we don't have any algebra we can really do here, right? One of our strategies in the past when we had zeros was to do something like factor things and cancel out factors, stuff like that. We don't have that option here, right? There's really not much we can do with that natural log and that polynomial in the denominator. But here's a little piece of reasoning we want to try. So let's look at these two functions. I'm just going to give them names. I'll take f of x is equal to 3 natural log of x. F prime of x is going to be 3 over x, and g of x will be x squared minus 1, so g prime of x is equal to 2x, okay? And then I'm going to evaluate each of these at 1, right? We know that f of 1 is equal to 0. We already saw that above, and same thing here, g of 1 is 0. Their derivatives aren't 0, though, at 1. The derivative of f is 3, the derivative of g is 1. So we can write linear approximations for both of these, tangent line approximations, right? So the tangent line approximation for f will be y equals, so our derivative and then x minus 1. Right, it's really y plus 0, but that's the value that we don't have 0, we're not going to write down. And then here we get y equals 2, x minus 1, okay? What we know is that near x equals 1, f of x is approximately equal to its tangent line, and g of x is approximately equal to its tangent line, which means near 1, f of x over g of x is approximately equal to the quotient of these tangent lines, right? We're just approximating things. And if that's the case, then the limits, at the very least, should be approximately equal to each other. okay? Now, let's notice what happens to this limit on the right. Right on the left-hand side, we got 0 over 0, but here, we're losing zeros. Those things these factors that would have given us those zeros, and we're left with 3 over 2, okay? Now, this isn't a rigorous proof, and we're not going to do that. You can find proofs out there. There are special cases that are proved relatively straightforward, but to prove this in full takes a little bit of work that we're not going to do, but this intuition is going to work for us here. The limit here is turns out to be the ratio, right? 3 and 2, these are exactly, oh, I wrote this wrong again. Boy, I'm full of errors today. G prime of 1 was 2. I wrote it correctly here. I think it said it correctly. That ratio is the ratio of these derivatives evaluated at that point, which is just the limit of these derivatives evaluated at that point. And this is what L'Hopital's rule tells us. Well, let me look at a picture first, and then we'll write down L'Hopital's rule. Here's a picture of the function, the natural log, 3 natural log of x and x squared minus 1. The red is the natural log. The blue is x squared minus 1. Here they are both going through 0. So when we took their quotient, this is the zeros that were popping out. And what we've done is instead looked at their tangent lines, these dotted lines, which look very similar at this point. And so the quotient of those tangent lines ends up being equivalent enough to the quotient of the function so that in the limit, they turn out to be the same. So let's state L'Hopital's rule, at least one part of it. So L'Hopital's rule. And this is for the case when we have 0 over 0, okay, as our limit, okay? There will be other cases, right? So infinity, plus or minus infinity over plus or minus infinity is another case. There's a few other cases out there, but we're going to start with this one. And the rule can be stated as follows. Suppose f and g are differentiable functions on an open interval, containing a, this is a point A, a value, an x value A, possibly not at A, whoops, let's put a period there. If the limit as x goes to A of f of x is equal to the limit as x goes to A of g of x, and they're both equal to 0. So this is just saying if both limits are equal to 0, then the limit as x goes to A of f of x over g of x is equal to the limit as x goes to A of f prime of x over g prime of x. Okay, so this tells us that if we're taking a limit, it has this indeterminate form, 0 over 0, all is not lost. We can take the derivative of each function, the numerator function, denominator function separately, and look at the limit of those as we approach A, right? We don't do the quotient rule. We have a quotient here, but we're not taking the derivative of this quotient. We're using this fact that the ratio of the derivatives and the ratio of the functions when our limits are 0 over 0 look the same enough near 0 or near this point that we can substitute one for the other, okay? Notice this works assuming the limit on the right exists, right? So that has to exist for this to work. Also, this holds if we replace A with So I'll write a plus, a minus, meaning we can do this as a one-sided limit as well, if that's something we're interested in. This also works if we're taking limits at infinity, positive or negative infinity. So these limits can be x going to a number or positive or negative infinity, and this rule will still hold. Let's do an example. Early in the quarter, we looked at the following limit. The limit as x goes to 0. This is one of our very first videos, very long ago. And we used geometric reasoning to determine that the limit of sine of x over x as we go to 0 is 1. Okay, so we went through this somewhat lengthy argument to show that that's the case. With L'Hopital's rule, this is a very simple thing to show. We know that if we look at the limit, let's say it this way. The limit as x goes to 0 of sine of x is equal to 0, and the limit as x goes to 0 of x is equal to 0. So we have this first condition, both limits are equal to 0, then this limit here must be equal to the limit of their derivatives. The derivative of sine is cosine of x. The derivative of x equals 1. And now we can simply substitute 0 in, right? Because cosine is a continuous function, so we know that we can just put in 0, and cosine of 0 is 1. And so without all that geometric reasoning, right, we can get a pretty straightforward answer to this limit this way. Okay. All right, let's do a couple more examples. Let's look at the limit as t goes to 0 of e to the 2t minus 1 over sine t. Oh, sorry, well, we'll do it this time. So let's first note that the limit as t goes to 0 of e to the 2t minus 1, well, we can put in 0 for t. We get e to the 0 is 1, 1 minus 1 is 0. And this is also equal to the limit as t goes to 0 of sine t, right? We've already worked that one out. So that means we can take this limit as t goes to 0 of e to the 2t minus 1 over sine t, and just take the derivative of the numerator and the denominator separately. Again, not the quotient rule. It's much simpler than that. We simply take the derivative of the numerator and the denominator. Derivative of the numerator is 2e to the 2t. Using a little chain rule there, the ones, oops, I forgot my limit. Let's put that in. The limit as t goes to 0, and the derivative of sine is cosine. These are both continuous functions, so we can simply evaluate by putting 0 in there. Cosine of 0 is 1, e to the 0 is 1, and we end up with 2. So what I started to say that I wanted to mention is I haven't seen a standard notation for this, but what I like to do is leave myself a little mark when I'm applying L'Hopital's rule. I do this so that if I make an error, sometimes I put a little, I know it's on the wrong side. I should stop. I don't know why I ended up on the wrong side. It's a little clue to myself that if I make an error and I'm looking back over my work, I'll know exactly how I got there, right? If I took this derivative incorrectly and I was looking back over my work, I might be confused as to what exactly is going on. But this gives me just a little note to myself. You applied L'Hopital's rule here. It should be evident, but it's always nice to do that. And somebody else looking might also be able to decipher that. If I was writing a text, I would probably make the standard notation. But in any event, there is our derivative, or our limit. Let's look at both of these examples on a graph. Let's zoom out. Okay, so first we had our sine x over x, right? So here's that function. It's not defined at 0. You can see the computer is telling me undefined at 0. But if you look at that graph, the values are getting very, very close to 1 as we go there, as that first example showed us. Here is our e to the 2x over x, over cosine of x. And we're getting the same thing as it's undefined at 0, but we can see that the function's values are getting very close to 2 from either direction. Okay, it's a fun little function. Oops, I've got something else open. Okay, so there are those 2 examples. Let's do one last example to finish off this video. Let's look at the limit as x goes to 1/2, 6x squared plus 5x minus 4 over 4x squared plus 16x minus 9. Okay, so first of all, I want to look at the 2 limits individually. The limit as x goes to 1/2 of 6x squared plus 5x minus 4, and the limit as x goes to 1/2 of 4x squared plus 16x minus 9. And you can check for yourself, putting in 1/2 to both of these gives us a 0 over 0, which is indeterminate, which means I can apply, because it's that 0 over 0 case, I can apply L'Hopital's rule. So I will do this again. I get 6x squared plus 5x minus 4 over 4x squared plus 16x minus 9. Applying L'Hopital's rule, take the derivative of the numerator and the denominator separately. The numerator gives me 12x plus 5. The denominator gives me 8x plus 16. This is now 2 linear functions that I can just evaluate at 1/2. The 0 problem has disappeared, and I just use direct substitution. So 12 times 1/2 is 6 plus 5. 8 times 1/2 is 4 plus 16, gives me 11 over 20. And that's our limit of that quotient, that rational function. Okay. This is not the only way to do this one. I just want to point out this we could have done with one of our old methods, and let's do that and see if we get the same thing. So if we had noticed, we can factor the numerator and the denominator here. So if you do a little bit of work, you can rewrite the top, the numerator, as 3x plus 4, 2x minus 1. And the denominator is 2x plus 9, 2x minus 1. Right? Notice that factor 2x minus 1, if you plug 1/2 into that, you get your 0. That's where those zeros came from. It was that factor, right? You can multiply this out and see that these are the right configurations. But now, since we have factored it, we see that we can cancel them. Remember, our limit doesn't care about 1/2. So even though this is equal to 0 over 0 undefined at 1/2, the function without these 2 factors is exactly the same everywhere else. And so we have just the limit of 3x plus 4 over 2x plus 9, okay? Right, which is again 2 linear functions with no zeros there. It's not the same ones we got above. We've gone a different route, so things look a little different, but we can just use direct substitution. 3 times 1/2 is 3/2, plus 4, let's write 4 as 8/2, because we're going to need to add them together in a second. 2 times 1/2 is 1, plus 9. So I've got 11 over 2 in the numerator over 10, which is, of course, 11 over 20. Which we expected, right? These are both valid ways to compute this limit. They better come up with the same answer, or we have a process that's not well defined. Okay, that is it for this one. That was our introduction to L'Hopital's rule. There are some other cases, and we, as with most things, can make this much more complicated, but this gives us a really nice way to attack some of these limits that we aren't able to deal with immediately. All right, so this first example I think was very good. 3 natural log of x over x squared minus 1. There's not a lot where you can do with that natural log, but with L'Hopital's rule, it's a pretty straightforward derivative or limit to take. Okay, that is it for this one. Thanks everybody. I will see you next time.